So my name is Christian Schönberger. It's a great pleasure to introduce the next speaker, Stefan Hell from the Max Planck Institute for Biophysical Chemistry in Göttingen, and several more affiliations I've seen, among them the German Cancer Research Center in Heidelberg. So I very much doubt that Stefan Hell needs a long introduction, since he's very well known. He's a famous scientist, and most of you you should know him, actually. He's one of the pioneers who introduced what is today known as super-resolution microscopy. With his technique, he invented the stimulated emission depletion method, STET, and he received for this work many distinguished prizes and recognitions, among them the Kavli Prize in Nanoscience, together with Pendry and Ebbison in 2014, and also the Nobel Prize in Chemistry in the same year, 2014, together with Spetik and Mörner. So we're very pleased that you found the way to Basel, and we very much look forward to your talk. Thank you very much.
Thank you. Thank you very much. So thank you very much, Christian. I'm very pleased to be here, to be able to give this keynote lecture at this little meeting, and of course I will talk about microscopy and spatial resolution. There's no doubt about the fact that the visual perception is extremely important to humans, and therefore the saying, a picture is worth 1,000 words, or seeing is believing, not only applies to our daily lives, it definitely also applies to sciences. And therefore, it's not a coincidence in the development of the natural sciences that the beginning of the natural sciences in history very much coincides in time with the invention of the light microscope. Because with the light microscope, mankind was able to see for the first time that every living being consists of cells as basic units of structure and function. Of course, with light microscopy, bacteria were discovered. However, I'm sure you learned in school, as I did, that the resolution of a light microscope is fundamentally limited to about half the wavelengths of light, which typically amounts to about 200 nanometers. And if you want to see smaller things, you have to resort to electron microscopy. Now, electron microscopy has provided a higher spatial resolution. As a result, mankind was able to discover viruses or important subcellular organelles and protein complexes. And in a number of cases, with electron microscopy, you can get a resolution that goes down to the molecular scale. And therefore, if you're a physicist by training, as I am, the question comes up, why do you still bother about the light microscope and the spatial resolution of the light microscope now that we have the electron microscope? Now, the answer to that question is very easily given. Here, I vindicated the importance of the light microscope just by counting the number of papers that were published in this issue of Nature Medicine. And you see, if you count them, which of the two methods won, electron microscopy versus light microscopy. So it's a fact that light microscopy still is the most popular microscopy modality in the life sciences, in basic medicine. And as you certainly know, because of two good reasons. Now, the first reason is it's the only way by which you can look into a living cell, especially into a living cell in 3 dimensions with minimal invasion, so you don't harm the cell. This doesn't really work with electron microscopy because usually you have to dehydrate or evacuate and so on, and there are problems, of course, if you want to look into living cells, for example. But there's another reason, which I think is even more important or equally important. Of course, we know by now that there are cellular organelles and all kinds of things, but we would like to know where proteins are located and what they do and with which proteins they interact. And to light, of course, and also to electrons, all the proteins look the same, despite the fact that 10,000 different types of proteins, species of proteins. And so we have to make them distinct if you want to study a certain type of protein. And that can be done very easily in a light microscope and not so easily in an electron microscope. Namely, you can highlight the protein of interest just by attaching a fluorescent molecule to it. And the fluorescent molecule, of course, makes that protein species distinct by the fact that it's labeled. And then, of course, if you shine light on the fluorescent molecule has an energy ground state and an energy excited state. If you shine, for example, green light, then the molecule will be raised to a higher lying state. Here, the high lying state will last for about a nanosecond or so, and then the molecule relaxes to the ground state, again emitting a fluorescent photon. Now, because some of the energy is lost in the movement of the atoms upon absorption, the fluorescent light is redshifted, as we know. So it is orange in this case, and therefore it's very easy to separate the fluorescence light from the light with which we illuminate the cells, and that makes fluorescence microscopy extremely sensitive. As a matter of fact, you can label a single molecule, of course, single protein with a fluorescent molecule, and then in a cell, and you can still detect that single molecule in the context of the whole cell. So the sensitivity is enormous on the single molecule level. However, if there is a second molecule, a third, fourth, or a fifth, coming very close to the first one, you cannot tell them apart. So the resolution is not sensitivity. You must not confuse it with sensitivity. The resolution is about the ability to tell features apart, to recognize that molecules that come closer together than a certain distance are still two molecules or more molecules, that you can distinguish them as separate entities. And this was the problem. So any sort of detailed information, structural information that was finer than the 200 nanometers couldn't be sorted out with light microscopy. Therefore, it was obvious that if one manages to overcome this barrier, at least for fluorescence microscopy, then this would have a substantial impact in the life sciences. Now, you may ask, why do we have this diffraction resolution barrier? Why does the light microscope not image more, say, details that are smaller than that? The different ways of explaining this problem, the most profound way is in fact the simplest way, and I'm explaining in the simplest way just to make it clear that this is also the most profound way. You can say that the most important element of a microscope, a light microscope, is the objective lens. And the objective lens is nothing but a lens, and the role of a lens is to concentrate the light in space on a single point. However, because light propagates as a wave, as we know, it's not possible for the lens to concentrate the light on a single geometric focal point. Rather, the light will be smeared out in the focal region here, forming a blob of light that is at least 200 nanometers wide and about 500 nanometers along this axis, as a result of diffraction, as a result of the wave nature of light. And the consequence of this phenomenon is very profound. Everything, so every detail, every molecule, let's assume these are molecules here, or vesicles, or whatever, that fall within this minimal range of focusing, within this spot of light here, of illumination light or excitation light, will be flooded at the same time with light. And hence they will also fluoresce at the same time, more or less, because they are flooded simultaneously, because they all reside within this spot. And so if we try to measure the fluorescence of these molecules, then of course it will be messed up. Why? Because if you collect the light here from with the lens and put it back onto a detector, each of the molecules, of course, will also produce a blob of light, because light is also focused here at the detector, and then the neighboring molecule will also produce a blob of light, and because they are so close together and fluoresce at the same time, also here the light will overlap in space. And it would not be possible for the optical microscope to tell that signal apart, no matter what detector we placed in here. It could be a photomultiplier, could be the eye, or even a pixelated detector such as a camera. They won't be able to tell the signal from the molecules apart, because we have these large blobs of light that result from the fact that we have here this phenomenon of diffraction. Now, several people realized this problem at the end of the 19th century. This man was the one who really understood all the consequences, made the world aware of it in stone. And this is what people believed, actually, throughout the 20th century. It was well accepted that if you have something closer together than this, at the end of the day, you won't be able to separate it using focused visible light with regular lenses. Not only it was a belief, it also was a fact. So when I was a student in physics, actually, at the end of the 80s in Heidelberg, I was asked to look into image formation of light microscopy, of confocal microscopy to be precise. So this is the high end of resolution that one could get at that time. So this is an image taken from a cytoskeleton of a mammalian cell. And so you see there is many details that are obviously not resolved. This is why it looks so blurry. Now, the development of STAD microscopy, about which I will talk in a few minutes, has shown that you can overcome this limit. I think this is the most important merit. It showed that there is physics, so to speak, in this world, or there is nature gives you phenomena at hand by which you can, at the end of the day, distinguish things at much higher spatial resolution. So it's not true that there is no way to do it. There is physics that really gets you there and shows you a level of detail that is clearly beyond Abbe's barrier, and therefore you can see new things. Now, this discovery that you can overcome this diffraction barrier has had a number of consequences, of course. And a consequence that it had for me, and for me it had substantial consequences, 1.5 years ago, and it was mentioned in introduction, is that I had the privilege of meeting Scandinavian kings. And the first king I had the privilege of meeting was King Harald of Norway, handing me out the Cavalry Prize for nanoscience with Thomas Ebbison and John Pendry with a scroll and a very nice medal. And about 4 or 5 weeks later, I got a call that I would have the honor of meeting his neighbor, the Swedish king, together with Erik Betzig and W.E. Myrna, again with a very, very nice scroll and very nice medal. And this was followed by a banquet, quite impressive, with very good food. And very nice company, actually. But I'm sure you're not interested in the gossip and this type of thing. You want to know how this diffraction barrier has been overcome and what can we do with it today and what's my perspective on that. So I will definitely talk about this. But I thought that it's maybe, since this is a kind of keynote lecture, it's also a good occasion to talk a bit about the history of the discovery. And in many cases, I think if you discover something or develop something that really changes the mindset of people, it's very often connected with the person that makes the discovery. And this was clearly the case in my case. So I'll talk a bit about my trajectory in life. And you will see how that was intimately connected actually with what I did. So I was born actually in the western part of Romania, German ethnic in fact, because my ancestors came actually from in the 18th century from southwestern Germany to that part of the world, which was in those days part of the Austrian Empire. But I grew up, of course, in a communist country. I realized that as a minority, it's not so easy to live your life properly. So I convinced my parents at the age of 13 to get out of communist Romania and go to West Germany. So we went actually to Ludwigshafen in West Germany. My mother was a bit scared. She wanted to be west of the Rhine, and so because far away from the Iron Curtain. And I liked the place because it was close to Heidelberg. I knew Heidelberg is a great place to study, and so I wanted to study physics in Heidelberg. And so after getting my high school leaving certificate, I enrolled to study physics in Heidelberg. And like most physics students, at least at that time, I was interested in basic physics, like fascinated by quantum mechanics, relativity, wanted to do particle physics, radical physics, and things like that, high aspirations in that sense. However, at the time I had to choose and to opt for my PhD thesis, I kind of lost courage doing that because I talked to the older students. I said, you should not do that. You should not do theoretical physics. You end up as a taxi driver, and of course particle physics. That's something that's not earn you a living. And this had made a lasting impression on me because, as you can imagine, we just came from the East, and my parents still had to struggle to settle in the West. As a matter of fact, my father got a job, but he was threatened with unemployment, and mother was diagnosed with cancer and eventually died. And I felt, okay, I should do something that really earns me and perhaps my parents a living. I should not gamble with theoretical physics. And so this is what I looked back then as a PhD student, believe it or not. I decided to sign up with an advisor, this is his name actually, a solid-state physicist at that time, who set up a startup in Heidelberg, and that startup that specialized in developing confocal microscopes for the inspection of computer chips and also for biological imaging and so on. And I was asked in my PhD thesis to sort out the imaging capability of confocal microscopy for the inspection of computer chips. And I thought, okay, if you do something with computer chips, you will easily get a job with Siemens or IBM later on and don't have to be worried to get unemployed. But I did it for 6 months. I started with it and realized, this is not what I wanted. This is a boring subject. I mean, this is the 19th century physics. There was nothing but lenses, a microscope, and light reflected. I mean, there's nothing nothing interesting. It's just that subject. And so just measuring the line width of computer chips, and there's hardly anything more boring. So I had, so what I did is I secretly shopped around asking colleagues, his colleagues, obviously, if there are other theses that I could do and drop it. That would have been one option. The second option would have been to become miserable, perhaps. And there was a third option. I thought, maybe there's still something cool that I could do with this boring subject of microscopy. But what is left? And so, the only cool thing that is left in light microscopy would be to break the diffraction barrier. Because everyone believes that's impossible, and this is something that will be worthwhile pursuing. And so I got this crazy idea, if you like, to look into the breaking of the diffraction barrier because I felt this is cool. I didn't care for life science. I didn't care for microscopy per se. I just wanted to know whether this is possible. And so at some point, I really got convinced that it should be possible for the following reason. I thought to myself, okay, now this diffraction barrier was coined in 1873 by Abbe. Now, that was 1889 or so. 100 years, more than 100 years had passed since then. So much physics was invented and found and discovered in the interim. Quantum mechanics, as I said, molecular physics, spectroscopy, all these things. There must be at least one phenomenon that has been discovered in the 20th century that could be used to overcome this barrier, at least for some type of microscopy. I didn't want to look specifically for fluorescence. I would have done it for anything. I wanted to check out if there's really no phenomenon that gets you beyond the barrier in a highly effective manner. And at some point, I became convinced that this is possible, and I realized it wouldn't work just by focusing the light better, because that had come to an end. I knew that. But maybe if you exploit the properties of the inflorescence microscopy of the molecules that you look at, exploit the spectroscopy of the fluorophore, maybe there's state transitions that could be used, or maybe there are quantum optical phenomena, because this was new at that time, that could be used to overcome the diffraction barrier. So that was my reasoning. And so I screened textbooks in the hoping that I would find something. But I couldn't do it in Heidelberg. I didn't find support. And so I was just about to drop out of science and become unemployed. In fact, I was for a brief time. But I was lucky that I met a person in the lab that I worked in Heidelberg who was a Finn. And he introduced me to a person who became a professor here in Turku, in Finland. And he said to me, okay, if you come to Finland, to this place that I had not heard of before at that time, I must say, you can work on your crazy idea, and you get some freedom, and you have to help me setting up your startup company in a way, because you want to set up a startup on immunoassays. And so I ended up there in Finland, and with some support of the Finnish Academy. And I was there for about a couple of weeks in '93 with this idea of there must be some way of overcoming this barrier, with this idea in mind. And I screened this textbook one Saturday morning, and then I opened this page, and then I found this word here, or this phrase, stimulated emission. And then all of a sudden, I got totally excited. I felt, oh, this could be a phenomenon that really gets me beyond the diffraction barrier. So this is how I got the idea. I was totally excited, went to the lab, and made some simulations. There was no laptops at that time, so I had to go to the lab to make computations. And now I'm showing you why I was so excited. Of course, it's clear that you cannot change the fact that all the molecules are flooded with green light, with the excitation light. That's clear. You cannot change that, because that's the results from focusing. But if you manage to put the molecules in a state in which they're not capable of sending light back to the detector, of not producing light here, if you put them in a dark state, then, of course, you would see only those molecules that are in the bright state, that remain in the bright state, and the dark state molecules you won't see. And if you do that with all of them, but that one, you would just single out that one from the rest, and you can discern it from the rest. So the idea was to play off, to turn the molecules off here transiently, just to see those, despite the fact that all of them are flooded with light, say, look from the top, only that one is allowed to emit. And so the idea was to keep molecules in a dark state. And now you would say, are there such things as dark states in these fluorescent molecules? Well, So the idea really is to play with the states. Well, look at the energy diagram. You have the ground state, you have the excited state. If the molecule is in excited state, the molecule flashes. So the excited state is a bright state. But the ground state is, of course, a dark state, because if the molecule is in the ground state, it's dark, and it does not fluoresce. It's very obvious. And so guess what simulated emission does, and why I was so excited? It just makes molecules go to the dark state. So while you can excite molecules, of course, with green light, you can also de-excite it with redshifted light, which is a phenomenon called simulated emission. The molecule instantly ends up here in the ground state, which is a dark state, and cannot fluoresce and send its fluorescent light back here, because it has been sent down to the dark state. And so this was the idea: keep molecules dark. And so this has led now to the design of this STET microscope. It's very simple, in fact. You have a lens, you have a sample, you have light for turning molecules on. From the off state is the ground state, the on state is the excited state. You green light, turn them on. And of course, if you have the light will be diffracted here, and all the molecules will fluoresce. If you have many of them and produce light here, and the resolution won't be better than in Abe's case. But now, of course, we also have a light that turns the molecules off, just does the opposite. So this turns them on, and this turns them off. And so if you turn them off, they cannot fluoresce. That's simple. Now, the condition for turning molecules off is that, as I said, the wavelengths has to be redshifted so that you don't excite them with the same light, with the same wavelengths. And there's another condition. Of course, you have to make sure that the beam is bright enough so that there is always a photon, so to speak, at the molecule that turns them off. If the red beam is very, very faint, of course, there will be many cases where there is no red photon to turn them off once they have been turned on. So you have to put in, within that nanosecond of lifetime, a photon that makes sure that the molecule goes down. And this is actually shown in here. So this is the intensity of the red beam, and this is the fluorescence ability of the molecule. And it's clear that the brighter the red beam gets, the more unlikely it is that the molecule can still emit in the presence of the green beam. And you can say arbitrarily, if I'm placing a threshold in here, that I'm placing arbitrarily in here, if the molecule is exposed to a red light that is beyond the threshold, you have turned the molecule off. It's off, 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 no matter how much green light you put in it, because there's always a red photon that pushes the molecule off, that pushes it down. And so you can play on and off with a molecule, with the ability of a molecule to emit. You switch it off by the presence of the red beam, simply by applying an intensity that is as high as the threshold, or of course higher. That's the same thing, of course. Now, with the red beam focused into this region, we would turn off all the molecules. That wouldn't make any sense. So what do? We modify the beam such that not all molecules are turned off. And this can be done in one way of doing it. The most reasonable way of doing it is to convert this beam into a ring, just by putting a piece of glass in here that converts a beam into a ring. So it's not focused into a spot, into a disk, it's focused into a ring. And now we turn off the molecules in here, but of course the intensity decreases, of the red light decreases, and here it goes to 0. And now while we could turn off molecules here, we wouldn't be able to turn them off here and here, because the red beam is too weak in this sketch. But let's assume we would like to see the molecule just from the center. What do we have to do? It's very simple. We just have to make the red beam bright enough so that in absolute terms, it's beyond the threshold. So although it's here only 50% of the maximum value, the maximum value is found here, it's only 50%. In absolute terms, it's beyond the threshold or at the threshold, and then we turn the molecules off in this way, and only those molecules here are allowed to emit. And now we can discern, of course, features that are closer than the diffraction barrier, because molecules that are closer than this distance given by the size of this green region here are forced to emit sequentially in time. So this is what happens, because they are forced to assume the on state sequentially. They cannot assume the on state here, because as soon as they get up, they're instantly pushed back down to the off state. And so this was the idea. Published in 94, I had it already in 93, and so you may say, okay, great idea. People say that, go ahead and do it, and that's it. That wasn't the case. Actually, I went around for 3 years to US, to conferences, paid out of my own pocket to a large extent, telling this idea, but no one believed in it really. So it was very difficult to survive. At some point I survived just by selling patents to mid-sized companies, and they said, okay, we give you some money, down payments, and in return, of course, we would get benefits if it works out. And so, well, it was not easy, but I should say that I was much happier during this time than during my PhD season because I worked on a fascinating problem. So it really shows a lesson that one should work on the things that one really likes and not the thing that one is supposed to do, believes that one should do because it earns a job or I don't know what. And so I was really fascinated about that, and eventually somebody has to rescue you. And so I ended up in Göttingen because there were a group of directors there at the Max Planck Institute. They said, we're not sure if he's right and this barrier can be overcome, but if you don't give him the chance to do it, we will never know if it's possible. And so I got it to work here for 5 years, non-tenure track, by the way, job, and it turned out to work. And this is just an example of, well, these are nuclear pore complexes before and after. And because the resolution here is increased roughly by an order of magnitude, you see details here that, that are not visible in normal confocal microscopy. You see the 8-fold symmetry of the nuclear pore complex here. I must admit I like comparing it with the standard confocal, despite the fact that it's clear that it works, but still have a lot of joy doing that. Anyway, so not only you get clearer pictures, you also learn something. And I'm showing this application, why? Because it's the first in this field. Meanwhile, many more have been done. So it's the first application in the field of virology. So together with a colleague who is an expert on HIV, Hans-Georg Kreuzlich, we looked into the distribution of a certain protein called ENF on an HIV particle. If you look confocally, you don't see anything if you label the ENF, because it's just a blob. If you take a stat picture, then you see that this ENF makes all kind of arrangements, patterns on the HIV particle. And so what has been done here is a correlation with the maturity level of HIV show that in mature HIV, the ENFs are focused in a single spot, so to speak. This seems to be important for the particle to infect the next cell. Or you can see moving things, like here the synaptic vesicles in living hippocampal neurons at a high resolution, 70 nanometers in this case, roughly 28 frames per second. So it's the first application showing that you can look into living cells and you can see dynamics. The speed is limited just by the brightness of the fluorophore. So it's not the technicality of scanning that limits your speed. It's the brightness of the fluorophore. So the better the fluorophore, the faster you can go. Lifestyle imaging at the extreme is if you go to a living system. And if you look at the upper, so-called molecular layer of the brain, you can see, for example, if it's labeled, of course, a neuron, a stretch of dendrite here. This has been done in an anesthetized living mouse. And so these are the dendritic spines. Here there's the synapse. You can see movements of these little organelle, morphological features. And so you need a higher resolution in order to see these little movements. And again, this was the first application to a living system. This can be done better, of course, and there's continuing progress, making things better and faster and more sensitive and higher resolution. I think eventually it will be possible to see the proteins directly on the synapse, and this is also an important application. You can focus into the brain tissue and get a three-dimensional rendition of a neuron, as it is shown in here. So this is again actin and its three-dimensional arrangement. Okay, I would like to stress the STAT was the first method. So the STAT, and the important merit of STAT is not only that you can apply to fluorophores and in the normal way like you would apply a confocal microscope, it changed the mindset of people. Because it's very fundamental. You turn molecule on just by excitation, then you have a beam that turns them off. There's nothing more fundamental than that. You have just two basic states of a molecule, and this phenomenon can be done with any fluorophore. This is also important. Now, but it doesn't mean that it's the best in all cases, because the discovery was not that you can do stimulated emission for improving the diffraction barrier. The discovery was that you can play on-off with a fluorophore and hence get a high resolution. And this was clear to me from day one. So I realized that there's also other mechanisms for turning molecules off, like pumping them to a dark state, long-lived dark state, or making cis-trans isomerization to play out the on-off game with, say, atom relocation here. And so these all are alternatives to stimulated emission. And so I couldn't have called it STAT anymore, so I had to give it a different acronym because there's no stimulated emission in it. And you may ask now, why was this important to show that it's more general, not just stimulated emission? After all, this is very basic, and these are very special transitions, like dark state or cis trans doesn't work with any flow for. You have to have a flow for restrictions, unlike here. It's very simple. We separate by on and off, on and off. So this is the way we do it. That means that we want to have this molecule on when this one is off. And this is the way we separate it. But if the lifetime of the involved states, on and off, are very short, then it quickly disappears, the difference in states, quickly disappears. So the longer the lifetime of the on and off states is, the easier it is to create this difference in states and the easiest to read it out. And that means, so if I have long lifetimes involved, like cis trans, it stays there for a long time. It's optically bistable, as one would say. There is no reason to hurry up putting in the photons or reading them out, so you can operate at much, much lower light levels. So the light levels here that are needed to break the diffraction barrier with cis-trans isomerization are by orders of magnitude lower than in STAT microscopy. And this again shows that the breaking of the diffraction barrier is not a matter of intensity. It's a matter of introducing an on-off transition. And so we looked into developing this concept, which is actually a derivative of the STAT concept because it operates at much, much lower light levels. And fortunately, it can be implemented with so-called switchable fluorescent proteins. And this has led actually to an implementation where many, many, many donuts, so to speak, or holes here can be used in parallel because you need very little intensity. I have a CW laser that is, say, spread out over a large field of view. And you see that the molecular transition is the actual issue that counts. The molecular transition determines actually the performance. And then, of course, if the distance between the holes is further away than Abbe's barrier, you can parallelize it. You scan in this direction, these multiple beams, and you scan in the other direction. And then in the end, you can take a large cell recording of a living cell in 2 seconds or even less, say with 100,000 of these holes even at low intensities. And this is really showing you that it's the transition that matters, and you can do much more. And STAT is just the beginning, as I said. Well, initially, it looked all like this. So it was setups that had to be carefully groomed and optically aligned to see if this phenomenon works. Because people said in the 90s, he will end up like the false prophets that were there already in the 50s, 60s, and 70s that all promised high resolution but never worked out. But this worked out, not only in the lab, but also in commercial systems. So there's a bigger company, there's a smaller company. I must admit now that I have shares in it, and the smaller company also has released a commercial system. And I'm proud that this picture actually was taken with this small startup from Göttingen. And this was the official picture of the Nobel Committee for the poster. And here you can see it, and they explain the STAT microscope in detail. And they also explain the other microscope that was demonstrated 6 years after STAT, in fact. It rests on the very basics. It rests on the same principle. It also plays on-off with the molecule. It uses the same transition like cis-trans, but on a single molecule level. So this is the Palm principle that was first implemented by this man, Eric Betzig, and W. Myrna was the man who saw fluorescent molecules or molecules first, single molecules first, and so I have the honor of sharing the prize with them. But in the end, the whole story, if you want to put it in a nutshell, if you ask him what's the essence of the discovery, is that you can separate features now by playing on and off with the fluorophore. So you have many fluorophores, and they're very close. You cannot separate. What do? You silence them all but one, and then you can separate that from the rest. This is the basic idea behind STAT or PALM or STORM, and there are many other variations of the story, but in the end, it all boils down to this transient state transition where you make sure that not all the molecules emit, despite the fact that all of them are flooded with light. So while in the 20th century, it all boiled down to making sharp lenses. So if you asked in the 20th century, what do I need to have in order to have the best resolution? The answer would have been lenses. Go to Zeiss or Leica or whatever to get the best lenses. But now, this time is gone. This is important to understand. If you want to have the best details, you have to have the best fluorophores. because it's the flow force that now allow you to make the separation. You play on and off, and the better this on and off contrast is realized, the brighter they are, or the more often they go on and off, the closer you can put them together. And so it's not the lenses anymore that determine the resolution. It's, in essence, it's the molecular transition within the fluorophores that one has selected. So, and this can be actually spun out. You can say that one can expand this to absorption, non-absorption, scattering, non-scattering. It need not be fluorescence by definition, but it's easier to play on and off with fluorescence because it's easy to disturb fluorescence emission and get it back again. So what happens now with Abbe's equation? Well, it's not very difficult. So we made a little experiment many years back where we just looked at the sample, and you see now put on, this was the normal resolution, put on the donut and made it higher, the intensity, and then event resolution got better, so this is the resolution. And you see now one can jump over the diffraction barrier. So one, depending on the intensity that you have, you can scale the resolution, so to speak. And then if you put in the numbers, you will see that the resolution scales now inversely with the square root of the intensity of the donut crest over this threshold intensity, which is a feature of the molecular transition, of course. And this number is just here that we don't divide by 0, and I over S is a number like 1, 2, 3, 4, and even higher. And this is also a practical advantage. So for those of you who really want to apply super resolution, you should know that a method such as STAT or resolved really allows you to tune the resolution. So this is raw data of Apple fluorescence, and then now if you increase the intensity, you see now it becomes sharper. And so you can tune the spatial resolution like that, and you can adjust, of course, the spatial resolution to the need that you have. What's the drawback of having high spatial resolution? It's very simple. You have to scan more densely. That means it takes more time to acquire the data. Why? It's very simple, because you play on-off. And if you turn many molecules off in order to see the rest, you have to turn them on again in order to see them. So this on-off game is always at the expense of time. So that's the drawback that we have. But still, you can take decently fast images if you have the right implementation. And so, the difference is very obvious. And this picture is taken just by a push of a button, just by scanning in that sense. It also should not be forgotten, makes it easy to use. So we know what to do now with this equation. It's very simple. We plug in the square root factor, and this is now very convenient and nice because it means that it goes down in the equation to 0, but in fact to the size of the molecule, to the molecular scale. And in the end, if you ask me what's the point of the whole story, I told it already. We can separate this fiber from that fiber. Why? Because at the time the molecules here were on, those were off, and vice versa. And this is why we can separate them. So this long story was actually cut down to a very, very simple discovery. And so these are the people who have contributed to this development, had a lot of fun. Many of them are professors themselves or ended up in the startup company. Some of them are still in my group. And I would like to highlight them here. I would like to thank them for their contributions. And finally, there's one little thing at least for the younger generation of you should not forget. It wasn't this guy who made the discovery. It was this guy. Thank you very much.
Thank you very much for this wonderful talk and insight. I'm sure there are questions.
Who breaks the ice?
Oh, here. There is one question here.
Yeah, you said that there is another method with the changing of the transformation from cis to trans, and I wanted to ask, how is this done, changing the conformation?
Right. So this is done optically in this implementation, which we call resolved. This is the acronym. You can have a switchable fluorescent protein that is reversible switchable, and you can, for example, you can turn it on at a certain wavelength, say 400 and something, and then you can turn it off at another wavelength, say 488 or 520 or so. And in the ideal case, you can read it out at yet a different wavelength. So you can play on-off with 2 different wavelengths, and then read it out at a third wavelength. In a number of cases, it's degenerate, meaning that the wavelengths with which you read out also turns the molecule off. that happens, and then you have to have a molecule that's bright enough that if you read it out, it gives enough fluorescent photons before it turned off. But it is done optically in most of the cases. It's not necessary that for every transition you have an optical transition. For example, you can also have a molecule that comes back thermally, but you turn it off optically. That would also be a way. There's many ways of playing them out. But the decisive point is that the fact that the states are long-lived gives you time. I mean, it's still on the microsecond scale or millisecond, it's still fast, but not on the nanosecond scale. And because you have time, you then don't have to hurry up putting photons so quickly to turn things off or turn things on. And then that reduces the intensity requirement by orders of magnitude. And this is why this has been developed. And it's still in the process of being developed.
Other questions?
How do you try with other kind of fluorophores like lanthanides or quantum dots?
Yeah.
Will this picture change?
Yes, quantum dots has been done, at least with a certain species of commercially available quantum dots, red-emitting quantum dots. The STAT principle was demonstrated. Lanthanides, actually I started out with lanthanides because the place I worked in Turku, there's a company that specialized in lanthanide-based immunoassays. And so there was a lot of lanthanide chemistry there. And the problem with lanthanides is it's a practical one. They are faint. I mean, they have a long, this rare earth transitions, have a huge lifetime. There's very few photons that come out. I'm not saying that it wouldn't work in one way or the other, but that deterred me from implementing it, the low fluorescent yield. Push the button.
This one?
Yeah.
I was just wondering if it's also a possibility, instead of switching on and off the molecules, to sort of slowly move a sample into a beam of light and record the increasing fluorescence.
Something similar has been done. The method is called PAIN, so there are many acronyms out there, and it works like this. So you have, for example, a structure, like let's assume a microtubule, and you want to image that with high resolution. And so you have something, I have a fluorophore that is diffusing in the cytosol. And then, because it's diffusing so quickly, you don't get enough signal from it, although it's fluorescing. But then it gets attached to the microtubule that you want to see, and then it stays there for quite some time, and then it emits light. And of course, all the photons go to the same place at the detector and not diffusing around. So it's on. So it's off when it's diffusing because it's spreading its photons around, but once it's at the microtubule, it's on. It stays at the microtubule, it's bleached, and it's off again. And then you can locate that, of course, that molecule, as it is done in this Planck principle, and then you make a dot there and say, okay, here was my molecule. Then the next one comes, gets attached. So you can use binding and diffusion as a way of implementing on-off. You can say that if you have a physics background, even, of course, the coordinate or the space can be written as an operator. Even that is a state, so to speak. So even movement is a state. So quick movement versus arrested state. Yeah, and that can be used as a contrast. This has been done actually very successfully.
I'm not really sure if that's what I meant.
It's true. What you meant is actually to move the sample as an on-off. That wouldn't work because that doesn't give you a discrepancy between two adjacent features. I don't see how that works. But movement per se can be used as an on-off transition, but not of the whole sample.
What are the new theoretical limits?
The answer is it's the molecule itself. It's why? Because you separate by molecular states in the end, or by the pi conjugated electron system. And so the limit will be set actually by the entity that you look at, or that they use actually for separation, and that's the molecule itself. To be more precise, it's the extent of the pi conjugation of that electron in this polyatomic molecule, and that is of the order of a nanometer. So that is the fundamental limit of all these concepts, which is of course great because you had 200 nanometers and now you have 1 nanometer as a conceptual limit, which is the molecule itself, and it doesn't make sense to go beyond that, or even the molecule is kind of crazy, because in the end, you must not forget that what you look at is not the protein, it's the fluorescent molecule. The fluorescence microscope images only the fluorescent molecule, nothing but the fluorescent molecule, nothing else. So you cannot image the protein because it images just the label. And of course, you have to make sure that the fluorescent label faithfully represents the proteins that you look at. That's very important. So the 1 nanometer resolution is the conceptual limit, but in practical terms, for those who apply it in the life sciences, that's better than they need, in essence, or they need in the majority of cases. Put it that way. And so there are practical limits like the size of the linker and this kind of thing. But the conceptual limit is the size of the molecule.
And the best has been achieved so far?
You can quite close. Single-digit nanometer regime has been achieved in number of restricted cases, put it that way. And I don't see fundamental reasons why this is not possible. There is a question.
Actually, it's very related to what you just said. So most of the fluorescence microscopy, we're still limited with the choice of fluorophores we have got. And we don't look at the protein molecule itself or the molecule itself, but the dye. So could ever be fluorescence microscopy independent of fluorophores? Well, we can't call it fluorescence microscopy anymore, but could you see that coming?
If it's possible to do fluorescence microscopy without the addition of fluorescent molecules, external fluorescent molecules, well, there is some intrinsic fluorescence, of course, in a number of cases. But usually, what you do is you excite certain molecular states of native molecules. And of course, they don't want to be excited. They want to be in a ground state because at room temperature in a ground state, and no way to get them up. And if you get them up, they may just get disrupted. They may be bleached. They may ionize. They may I don't know what. And so in the end, you will cause a lot of destruction, like your skin burns or something. And so it's not very attractive. And so the scheme of adding a label that is susceptible to light it has been extremely successful at the expense of adding something externally and at the expense of having a distance between what you look at, namely the fluorophore and the protein itself. But I mean, I'm jokingly saying it's a luxury problem. I mean, 20 years back, people said, okay, anything that is below 200 nanometers, no way. And now we're talking about a couple of nanometers. I mean, come on. I mean, okay, but it's clear that if you want to go beyond that conceptual barrier, something radically new has to be invented. Maybe somebody comes up with something that is fundamentally different, but it's going to be hard. But I mean, before the diffraction barrier was overcome, people also said it's going to be hard, to never work. So I shouldn't say that. I mean,
yet a last question?
Yes. There is a mystery that probably could be solved. You can do things studying the living cells, and the mystery is macroscopically, for instance, the heart is very orderly. You can see that in an electrocardiogram. But microscopically, at the Armstrong level, there is chaos. And the chaos might explain the firing of the heart. Do you think that can be done with?
Well, I mean, certainly you can study cardiomyocytes like any other cell, and this has been done. In fact, where I work in Göttingen, there is a strong group doing this. And of course, you can look into various problems now, including at how collective beating comes about and so on, and how this is related to calcium signaling and whatever. It's not my field. There are endless applications, and it's up to those of you who have ideas and problems in mind to apply it. And I would strongly encourage you. So the thing that I would like to mention, maybe 5 years back, it would have been fair to say, this is very difficult to use, it's very expensive, and maybe only specialists can use it. And you need a PhD, perhaps even in physics to do it. This is gone. This time has gone. So by now, systems have become cheaper, they have become reliable in use, they have become push-button to a large extent, they are even getting better. You will see important developments taking place towards user-friendliness, and so this is going to be a standard technology in every life science lab in the world that takes itself seriously. So, and you should embrace that at an early stage, because you will get a lot of ideas that you can do, as you just mentioned, just by realizing that you can do it at a push of a button. Don't think it's something that's only specialist and you need to come to Göttingen and send you a sample or I don't know where. This time has gone. And this takes some time to realize, for people to realize, but this time is gone.
Okay, so I think it was wonderful that you showed us, or to the young people also here in the audience, that it's worth to try to break limits and to look forward to, break things which people believe are just there, right? And so super resolution microscopy is an extraordinary example of this. Grateful for you to come here, although there's the Lindau conference, as I learned.
That's right.
And I wish you a good trip to Bodensee then. Thank you very much, and thank the speaker.
Thank you.